Whoops.
Somebody talk about the military? What was it? What was that thing for?
I don't know. I hit the ball. Somebody wanted me to make a mic when Mike says literally bell. Hit the bell every time you say it.
I didn't realize I said literally that much.
I said the whole show would be like this.
That would be great if one day AI could do like a word counter, and we just had a competition to be like, okay, all right, here we have here's a list of common words that Bob and Mike say, right? Just like Bob Bingo. I know they've played Bob Bingo in your classes before. So which ones would you think are the most said words, and have like a competition to see like what are our crutch words? What are the things that we keep going back to?
That is funny. I would like that. Maybe we'll get a listener to do that. But
if they don't have the time to do that, if they do find that out and they want to talk to you about it, where can they find us?
Oh, well, you can just come on the Specialist Happy Hour and just put up your graphs and your charts and your pie charts and stuff like that, which you can find the fourth Thursday of every month at 1900 hours Eastern Standard Time. Just go to thehazmatguys.com/happy and you'll find us right there. It's a static place. And got a couple conferences coming up. We got Indiana, we got Oklahoma, and we have Florida. The next three on top of my mind. But there's many, many more. I think there's almost 16, I think, in the hopper right now for the next year. So we'll be out there. We'll see us.
So let's keep on marching down this factors that influence chemical dispersion.
Yes. So going along with that, just the generalized stability of an atmosphere, okay, it would change things. So like atmospheric stability is the measure of how parcels of air move vertically. Stable atmospheres tend to inhibit vertical movement, leading to less vertical dispersion of gases. In contrast, unstable conditions promote vertical mixing and can lead to more rapid dispersion. And how could you know if you have an unstable atmosphere?
Don't ask me. I'm not Al Roker. I have no freaking clue. We're just telling you the factors that affect it. I have no idea how to look at the atmosphere and go, oh yeah, look at that. There's some atmospheric instability or stability here.
Dude, you know what the funny thing is? Like pilots say that, and I'm always amazed by that. They go, yeah, we're going to have a little bit of turbulence over like, the Great Lakes or something. How do you know that?
Their radar systems allow to be able to see turbulence within the layers of the atmosphere. I'm pretty sure that's what it is. I'm pretty sure that they can literally see. That's why air. Damn it! No, do it because I got it.
I'm not doing it.
I literally don't even remember literally saying literally. If you remember years ago, air travel was a lot bumpier. And I think they move around the turbulence a lot more than they used to. I could be wrong. If we have a pilot and you want to be like, he's full of shit, he doesn't know what he's talking about, I'll readily admit right now that I am. It's just a hypothesis. All right. But I can tell you that there are factors like temperature inversions, which we've talked about in the previous episode, and lapse rate, which is the rate at which the temperature is going to change with altitude. And they play a significant and crucial role in determining whether or not the atmosphere is stable.
Now, it is one of the major key components in whether things are going to go vertical. Right, it plays a crucial role in determining the gas plume, and atmospheric stability is characterized by the temperature profile of the atmosphere with altitude. So there's three main stability conditions. There's stable, neutral, and unstable, each of which affects the dispersion.
Right. So let's take a look at a stable atmospheric condition, right? In a stable condition, the temperatures increase with altitude, creating a temperature inversion. Mm-hmm. Warm air is trapped above the cooler air near the ground, which forms this incredibly stable layer.
So this is going to affect the vertical mixing. It's going to be very limited. Gases released into a stable atmosphere tend to stay close to the ground and do not rise readily. The plume remains concentrated and can spread horizontally. Now, in this stable atmosphere, when you have variations in the wind speed and direction, depending on the altitude, that's known as horizontal wind shear.
And this creates turbulence at the top of that inversion layer, allowing some limited vertical dispersion.
Now, stable conditions can lead to accumulation of pollutants near the surface, especially, well, I'm not going to say especially, potentially creating a worse exposure risk in the immediate vicinity.
I think we would see something
area.
like this in the city. We'd be driving in, and sometimes it's a crystal clear day, and sometimes it's just a little bit, hazy and foggy. The stable atmospheres tend to, I think, give a little bit more haze and fog to what's around. Unstable atmospheres. In unstable atmospheres, neutral. Neutral atmospheres. Neutral atmospheres. I just jumped from one to the other. I prefer instability, so that's why I went with that. Literally, it's why I went with that. All right, neutral atmospheric conditions. In a neutral atmospheric condition, the temperature doesn't change significantly with the altitude, meaning the temperature is kind of the same as you go up, resulting in a very uniformed vertical mixing.
Yeah, and that's what you're going to get. You're going to get a very evenly dispersed, both vertically and horizontal.
And believe it or not,
release.
because of this, right, the plume's behavior becomes less predictable than a stable or unstable conditions because there's no wind to blow it around. You don't know where it's going to go.
Right. And with that, you're offered, they are. It's very evident on wind because that's the only thing pushing it around. It's just going to kind of, I don't know, like I always think of those blast cartoons of you'll see in like the If's the Book or something like that, where there's a bomb that went off and there's like a dome of expanding gases. That's what kind of sticks to my head
because of the way that it goes out.
So yeah, it's just kind of very creamy. It's equally going up and sideways at the same time.
Unstable now, Am I going to get yelled at for going to unstable?
Please,
okay.
let's do it.
Unstable conditions. Nope. All right. So unstable conditions is now the opposite of the stable conditions in which temperatures decrease with altitude. As you go higher, those temperatures are going to decrease. That means that the air near the surface is cooler at night than the higher altitude. I'm sorry, that the air is cooler in general than those higher altitudes.
Now, this is going to promote vigorous vertical mixing. Gases released into an unstable atmosphere tend to rise rapidly, disperse vertically, reducing ground level concentrations. For me, as the incident commander, I would be like, "Oh, I love this. This is getting it up and out
means that
very
it's
quickly."
A little bit quicker in the mixing and dispersion efficiency. That's, I think, kind of the word that would be used, is that efficiency to just be gone. Obviously, that's going to result in a more uniform distribution, and you're going to have a little bit better prediction pattern.
Right. So wind patterns would have an effect on the upward motion as well. So just keep that in mind, that it can affect a little bit of the gas dispersion.
Due to that instability, the wind goes up, it takes the product with it. All right.
Right.
Time of day is important.
What about the time of day?
Because again, now it's a variable being affected by a variable, right? The time of day can influence wind patterns. If you're ever on the shore, near the shore, in the morning, the wind tends to push away from the shore, and in the evening, the wind tends to come back towards the shore. Absolutely phenomenal if you're a sailboater. Not so good if you got a chemical release that you're like, oh, thank God it's going out to sea. The daytime heating, it generates these convection currents that help gases lift up and out, while nighttime, they tend to drop low, and that inversion clicks in, and it reduces the vertical dispersion.
I love it. And additionally, wind patterns may change during the day, affecting the direction and the speed of the dispersion. Now, terrain, on the other hand, this would play a lot of a role in dispersing, because topography and physical features of the landscape can impact how it spreads and behaves. Here's how terrain can affect chemical dispersion during gas
channeling and funneling. And we kind of touched on this before when we talked about how unusual the wind patterns in New York City would be between the buildings. That's not just a city thing. If you have terrain such as valleys, canyons, narrow passages, channels, they channel the winds and the currents through these, and it changes the movement of the plume. It can restrict lateral dispersion of the gases and cause the flow downstream to kind of operate unpredictably, literally.
Yeah, so this is going to cause higher concentrations released in chemical-specific areas, increasing the risk of exposure by nearby
not just
populations.
Changing the wind direction and speed, you can literally have terrain that obstructs and impinges movement altogether. Things like buildings, trees, structures, they're all going to prevent that gas from flowing from one place to another. That means you're going to have a buildup of material where these obstructions are. They may be able to rise up, they may be able to go through, but either way, you're going to get a lag in your dispersion in that area.
And so when you combine these things, all the aforementioned things that we were talking about, and you have, something like a tree or a huge rock, you might have different plume modeling for the back side of it, the leeward side of it. So it's the complexity is just building now.
Are these things that you have to be able to calculate? Absolutely not. But you need to be able to understand that it exists so that you can go out and you can be like, hey, listen, do me a favor. Like, see where that giant line of trees are. Let's just go check that and see where it is. Perfect example. That very infamous, and I'm going to forget the place. Yes!
Festus, Missouri.
We've been doing this too long. You take a look at that video and you have this field that comes out, and then you have a tree line, and then you have another field, and that tree line literally prevented the chlorine from spilling over into the net. Yes, that was a more
very
soundy
show. Yeah, I hit the wrong button. I should have hit this one. I should have hit that one. I didn't think of that one.
All right,
I'm very happy with the sound.
I'm telling you, if you're not watching the video, he is smiling from ear to ear, and he can't wait for a moment to use one of his sounds. Reflection and turbulence within the terrain, right? The terrain can create reflections that cause the terrain can create conditions that will cause reflection and turbulence. Good example of this would be if the winds were to interact with, say, like a hill or a mountain, it would create these little eddy currents that kind of travel unpredictably. And while they may help with the dispersion, depending on their location, it's really hard for us to say, okay, that is definitely going to end up going here.
Right. And this turbulence and these eddies and whatever are going to cause malformations, I will say, of the plume modeling. This is why people like plume model, like, oh, it's just like this is where the wind's going, so it should be like a teardrop. I hope you guys are understanding the complexity in getting a realistic plume model, because there are so many variables. I don't even know how they do what they do right now. You know what I'm saying? So like it's very impressive, but I want to communicate
in high wind patterns.
Now, the influence on wind patterns, terrain can also influence wind patterns. So during the daytime, the different heating of the slopes and the valleys. So you have one side that's on sun and the other side is not on sun. So this is going to change how the wind
and you don't even need to be plume modeling. You should have an idea of this. If these types of terrains are in your area, you should be able to understand how those local winds may affect where a chemical is going to go in almost any circumstance. Because as hazmat, we certainly don't get a choice as to where the leak is happening. It could be happening in a rural area. It could be happening in an urban area. And the terrain between the two is extraordinarily influenced by weather. It's extraordinarily influenced by the layouts of things like streets, street signs, buildings, roads, canals, bridges, all of these. They can help to literally trap the gas in urban areas. God damn it.
Yeah, so... and you have difference in like between a rural area and in a rural area where there is no large obstructions, such as a building or whatever, these might be influenced more by larger scale wind patterns. Like when you go to a wide open field, you have a much windier area, right? So, and again, the elevation of the release point and surrounding terrain can impact the gas dispersion. Wasn't it Jackrabbit? Didn't they do one plume release from like way up high, like 100 feet up or something? I know like that?
Jackrabbit 1 was a 1 ton, and then Jackrabbit 2 was. Well, yeah, I think they were both
it was on the ground.
But
didn't they do one on a tower?
They may have, but I don't think it was Jackrabbit. But you did get to. Well, it does.
That would change the dispersion.
Absolutely, and you know what you were saying before too. If you watch the Jackrabbit video, you can see the buildings that they set up, the street structures, all of those things had they had an effect. And I thesaurus literally, and now I'm going to use all different iterations of literally.
Oh, that's so good. I like that.
So, yeah, elevation definitely makes a difference. Bodies of water can make a difference, right? Terrains near bodies of water, like your lakes, your rivers, your oceans, they can have a massive impact on how the gases go, where they go. Water surfaces can reflect gases and influence their movement, while the presence of water itself can impact the chemical reaction and the dissolution of gas in cases like ammonia, which was something that we kind of talked about the other day, how ammonia tends to want to, suck on to any kind of water source and hang around there.
Right. Now, also the polarity of a chemical will influence its behavior during the gas release. Polarity is a property of molecules related to the distribution of the electric charge on them. So if more charge lumps up on one side, it's more polar. And don't please, I heard somebody thinking it's not like you're pregnant, whether either you're polar or you're non-polar. There's many gradations of polarity, right? So it's kind of like, think about it like gravity. Small planets have less gravity and big planets have more gravity kind of thing. So here's how the polarity could affect chemical dispersion during a gas release.
The solubility in water, it plays an effect, right? Because that is precisely what ends up happening with polarity. Polar molecules, they tend to be soluble in water a lot more than non-soluble molecules because of that magnetic differences. So when a polar gas is released, it is going to dissolve in some extent to the surrounding moisture and increase its reaction or interaction with the environment.
Now, just again, we went through this before, it was rainwater, which is 100% humidity. If it's raining, can your chemical dissolve into the rainwater, right? Or humid air, or this may aid in quicker removal from the atmosphere. Like it scrubs it almost in like a weird way.
But I mean, but then you're taking your plume, right? If you have a polar molecule and it starts raining, you're now taking it and you're just dispersing it in a totally different, like, oh, it's traveling down the road. Oh shit. Yeah.
Yeah, right.
Polar chemicals can interact with other chemicals in the atmosphere. They could interact with other polar compounds to then react, create something completely different that you weren't expecting.
Right. And so all these things, they change. We're basically making a form of an aerosol, right, which can affect the behavior and the fate of the released chemical. It also may result in the gas being removed from the atmosphere more rapidly or being transformed to different compounds.
What happened to your hand?
I just cramped. I don't know what happened. I got to drink more water or something. Anyway, I was like, whoa.
Some of the health effects of the polar substances, right? When you have a polar substance, it can get into the air. Although this doesn't really have to do with how the molecule is going to move. Just understand that polar substances, they can latch into the air greater. They tend to have a higher potential for toxic injury in the future because they're kind of just hanging around.
If you think about it, just like the polarity of it is like, will it absorb through your skin? Right. So a lot of the polar stuff, it gets to dissolve into body fluids or accumulate in certain environmental compartments and may give you some long-term impact on health and human ecosystems. Now, also, the polarity will check into your detection and monitoring equipment.
Important because we use plume modeling to predict where it's going to go, but we use meters to determine what the reality is that it is going. Another thing,
you got to think about like all the electrochemical. All of them, it'll suck in, and that's the end of it.
We talked about temperature pretty extensively. Would you agree with that? Yes, I can see you're getting irritated by the topic. You're like, enough. And I get it. It's not, there's nothing really sexy about this. We're talking about things that, are probably going to just be a thought in your head. But here's a thought in your head, not the temperature of the atmosphere, but the temperature differences between the chemical and the atmosphere. Kind of what we say with the thermal imaging camera, right? The effect of the thermal imaging camera is the relative difference between two chemicals. Well, the chemical itself is going to change how it interacts with the environment, especially in a dispersion model, depending on the temperature that the material is when it actually releases. Because, you're changing things about it. You're changing things like gas density.
Okay. Well, temperature is going to change the density, right? It's going to influence the density of the gas. Warmer gases are going to have less density and colder gases because the gas molecules have a higher kinetic energy and are more spread out. Warmer gases tend to rise more readily in the atmosphere due to its lower density, when a colder gas will be more dense and stay closer to the ground.
Which means that it is going to affect the buoyancy of the gas plume, kind of putting it in different terms in case there's one way that doesn't make sense, maybe another way can make sense. The buoyancy, that gas plume kind of bouncing up and down. So those warm conditions is going to tend to be a little bit more buoyant and it's going to rise.
I like it. And also, you got atmospheric stability, right? And so this is your turbulence kind of thing. The temperature is going to play a crucial role in determining the atmospheric stability because stable atmospheric conditions often associated with temperature inversions, where the layer of warmer air traps the cooler air near the ground. They're going to inhibit vertical mixing and dispersion.
Have a chemical release that's so large, like I don't know. I keep thinking of like those propane storage facilities where they've got huge tanks. Do you think that the temperature of the vapors coming off of there would have enough influence over the atmosphere? Like even on a localized level? Like, is it really? I mean,
I bet it would.
It's a factor to consider, but I wonder if this is one of those like, yeah, but in reality, is it going to change the atmospheric? Is it going to change the patterns?
I think it would. Like, again, maybe this is a poor analogy, but like when you get into the pool and you run around the outside of it 100 times and you get that whirlpool action going. Well, if a chemical is coming through, and you got enough of it, could it influence like streams? Like, can it move air? Because it's moving air. So something's coming in to fill it behind. I would think it probably could. At least temporarily knock it out of kilter.
Can change local, weather patterns. Hyperlocal. I'm talking hyperlocal, right? I'm not saying, I got a leak here in Port Jeff and it's going to start raining at Bob's house. It's local.
Right.